Hello everyone, welcome to this second course about Newton's laws of motion. Today we will cover about the third law of motion as well as the consequences that can be derived from the second law of motion. The second law of motion is the most fundamental law among these three laws. Now the third law introduces us to the concept of action, reaction and impulse. Action and reactions are actually forces, a dimension of force, and impulse is a product of force and time, the time interval during which the force occurs. And since we have seen from the previous video, Newton's second law states that the product of force and time is equal to the product of mass and velocity, which is the change in momentum. So we can say that impulse is the change of momentum. We will see that later. One important fact that we have to remember is that force always occurs in pairs because it is an interaction between two bodies. For example, motion of a spring. The two bodies in a spring system is the spring itself and the body attached with the spring. So force always occurs in pairs. The motion that the spring undergoes always occurs between the object to which the spring is attached and the spring itself. Since we know this, let us give a clear-cut definition of what the third law is. To every action, there is always an equal and opposite reaction, and the action-reaction pair acts simultaneously on different bodies. There are three very important keywords here. That is, for the action and reaction are always equal and opposite in direction. They act simultaneously on different bodies. So they are equal, they are opposite in direction, and they act simultaneously on different bodies. These are the three important keywords that you have to remember regarding the third law and action and reaction. Now let us understand the third law by an example. Let a body A exert a force F1 on a body B and a body B exert a force F2 on body A. So according to Newton's third law, we can state that these two forces are equal in magnitude and opposite in direction, right? Because one of these forces is the action, the other forces is the reaction. So the mathematical formulation is F1 is equal to the negative of F2. The negative sign implies that the forces are opposite in direction. Now these are in bold because these are vector quantities. So they're equal in magnitude but opposite in direction. That's why we have the negative sign. We have to now consider the following facts regarding the third law. The first is the forces always act simultaneously on different bodies. They do not act one after the other. They always act together at the same time on different bodies. I mean, as we said in the beginning, that the forces always occurs in pairs on two bodies. So the forces are simultaneous on different bodies in a system. The third law can also be derived from the second law. As I've said earlier, the second law is the most fundamental among these three laws. Students, I would like you to prove this yourself, that the third law can be derived from the second law in the comment section below. Give me the answer there, and if you can't, I will surely give you the answer later. Another important fact that we have to remember is there is no cause and effect relation between F1 and F2. That is, it is not that the action comes before the reaction or the reaction comes after the action, because as we have seen in the previous example, F1 and F2 do not occur one after the other. That is, F2 is not because F1 has occurred. Both occur simultaneously. That is what we have to remember. So there is no cause and effect relation between F1 and F2. Now, since F1 is equal to minus F2, we can write, if we take it to that side of the equation, F1 plus F2 is 0. So the resultant force of the system containing two bodies A and B, if we take the previous example, is 0. For this system, F1 and F2 are internal forces. Now, you have to remember one important fact in Newtonian classical dynamics. For a system, the internal forces always cancel out, and that is a direct consequence of the third law of motion. So internal forces always cancel each other out. Now, as I've said, the third law introduces us also to the concept of impulse, which is also a direct consequence of the second law of motion. Now, what is impulse? Impulse is a product of force acting and the time interval delta t, that is the difference in time interval, when it acts. It's actually the product of the force and the time interval on during which the force acts. The force may or may not be uniform. That is, it may be uniform force or non-uniform force. The acceleration may be uniform or non-uniform. That is what it means. So let us give a mathematical formulation to it. If the duration of force, that is the time taken by the force, is from t1 time to t2 time, and F is the force at any time t, and dt, that is the infinitesimal change in time, is the time interval, the force is given by the integration of F dt from the interval t1 to t2. Okay. Now let us see what the second law says. The second law states F is equal to change in rate of change of momentum, that is F is equal to dp. Now if we take dt here and dp that side, so F dt is dp, right? If we take integration both sides of this equation and integrated it with limits, that is from t1 to t2 and momentum from p1 to p2, we can directly arrive at the conclusion that F dt, integration of F dt, is, which is the impulse, is equal to the change in momentum, that is p2 minus p1. Now since the mass is constant here, so the velocity is actually changing, so the change in momentum is equal to the product of mass and the difference in velocity. So we can say that impulse of force is equal to the change in linear momentum. From this equation we can also see that F dt is actually the area under the curve if we plot t on the x-axis and F on the y-axis. The area under the curve, that is this area, for example this area, is actually the impulse, which in turn is actually the change in momentum. Okay, this is what the integral calculus says regarding such quantities. F dt is actually this area. F dt is actually a small part of this area. If we integrate F dt, this whole area is the answer. Okay. The unit of impulse is thus force into time. So we have force is kilogram meter seconds to the power minus 2, which multiplied with time gives kilogram meter s minus 1, or Newton per Newton second. In SI system, in CGS system, it is dyne second, or gram centimeter s to the power minus 1. Okay, do remember this important fact. Now students, we come here to the second part of our lesson, that is the consequences of the second law of motion. Now there are almost two very important consequences of consequences of second law of motion. The first consequence is the conservation of linear momentum. Now what do you mean by conservation of linear momentum? The conservation of linear momentum can be stated by this definition. If no external force acts on an isolated system, the total momentum of the system remains constant with time. That is, if we take the which states that if the force acting on a body is zero, that is the total force acting on a body is zero, the momentum, that is the quantity p, especially linear momentum, which occurs in a straight line, is constant with time. It doesn't change. Now how do I derive that? From the second law of motion. From Newton's second law, here you see I have a handwritten sketch. From Newton's second law, the net force is equal to the rate of change of momentum. Now if the net force is zero, the rate of change of momentum, that is dp dt, is zero. Now you know from differential calculus that if dp dt is zero, so we can write dp is zero, hence p is constant. Now p is constant thus with time, because dp dt is zero, so p doesn't change with time, so the differentiation of p is zero thus. So linear momentum is conserved. This is what we mean by that. So if there is no external force acting on a system, the linear momentum is conserved, that is, it is constant with time. Now this conclusion that the linear momentum is conserved with no external force acts on a body is also a direct consequence of the third law of motion. From the third law of motion, we have seen that the internal forces of in a system cancel out, that is, they are zero. So the net force on the body is the summation, the sum of the external force as well as the internal force. Since the internal force from the third law is already derived from the third law is already zero, and we have taken that the external force acting on the body is zero. So if both are zero, the net force is zero, which gives us to the conclusion that the momentum is linear momentum is conserved. Okay. Now, another consequence, we can give an example: firing of a bullet on a wall, the conservation of linear momentum. For example, let a gun fire n bullets per second with a speed v. Let the mass of each bullet be m. Okay. Now the force applied on the gun to keep it at rest is nmv, which is why, because if a gun shoots, as we have seen from Newton's third law, action and reaction occur in pairs. Okay, so um, to keep the recoil is given by the change in momentum, that is nmv. Now when the when the bullets hit a wall, the force on the wall is nmv, the change in momentum. Okay, now when the bullets rebound elastically, the force on the wall is 2 nmv. Okay, because nmv is the force on the wall. When they rebound, they have a negative value because they are in the opposite direction, so the total force is the difference between them. The difference gives rise to the positive sign, thus 2 nmv. Okay. Another important consequence of the second law of motion is rocket propulsion, or collision forces, or ejection of gases. Now, as we have seen in the previous videos and this video, we have all in these cases considered the mass to be fixed. But in rocket propulsion, the mass is variable. It changes with time. Okay. Rocket is an example of the variable mass problem. In a rocket fuel, the fuel burns and produces gases at a high temperature. These gases are ejected out of the rocket from the nozzle at the back of the rocket, and thus a forward force is exerted on the rocket. This is a direct consequence of Newton's third law. So let us give a mathematical formulation to it. Let us assume that m naught, or m0 as we can read it, is the mass of the rocket with its fuel at time at t equals to 0. In the beginning, at rest, mass of the rocket is m0, m naught. M is the mass of the rocket with its fuel at any time t. So at t equals to 0, the mass is m naught, and at any time t, the mass is m. So now the rate of ejection of gases is r, which is given by minus dm dt. Dm dt is the rate of change of mass, and minus sign states that the mass decreases with time. Okay, because the gases are ejected out, so they are being removed from the system. And Vr is the speed of gases relative to the rocket. Okay, the ejection of the gases, so the gases are ejected out, so the speed Vr is the speed of the gases relative to the rocket. Now, the upward thrust on the rocket, if one neglects gravity, the upward thrust means force. The upward thrust on the rocket, if one neglects gravity, is equal to the rate of change of momentum of the rocket. So the rate of change of momentum is mdv by dt. Since the mass is variable here and not the velocity, we can write that minus dm dt, and the product of minus dm dt and Vr is the rate of change of momentum. Now minus dm dt is r, so r Vr is the rate of change of momentum. So rate of change of momentum from the second law is equal to the force. So the upward acceleration of the rocket is the force divided by the mass. So minus dm dt Vr by m, so r Vr by m. Okay, so if we consider the effect of Earth's gravity, the net upward force on the rocket is r Vr minus mg. G is the acceleration due to gravity, 9.8 meter per second square. So the upward acceleration changes. The form is given by minus dm dt Vr by m minus g, because we divide both sides by mass to give the acceleration. So we derive at this formula at the end, because the mass ejected is m m is given by m, no, m minus rt, as you can see here. So thank you students for this lesson.